Okay, so I just wanted to spend today's class just talking about what we did and trying to emphasize kind of like the key points that we did in class. Okay, so this class was calculus, and we saw that there were two types of calculus. There's differentiation, and then there's integration. And these are things that you do to functions, okay? So you're given a function, you take its derivative, and basically what you're saying is, what is the rate of change of that function? You take the integral of it, and you're kind of adding up all you're looking at the total change over some interval. So they are kind of like twins of each other, like opposites of each other in some sort of sense. And so the most basic, let's have a look at what really is the most basic thing we did. We looked at functions, and remember, functions came either as some sort of table, so it came as numbers. I gave you a graph, or I gave you a formula. So let's have a look at a function. Let's take x of x. And let's just say 0, 5, 10, 15, 20. That's enough. Okay. And let's just say I'm just making these numbers up. So let's just, just say it's 7, 9, 12, 11, 6. Okay. So this is just, we're just measuring something. Okay. So one of the things I can do is I can take the derivative of it. Okay, and this is kind of like the first thing that we really ever did. And remember, to do a derivative at a point, you're just looking at rise over run. We're just looking at slope. And so we could go, okay, so the derivative at this point here, okay, we go from 7 to 12, so we raise 5 over a run of 10, so the derivative is a half. Here, we go from 9 to 11, we go up by 2 over a rise of 10, so that's 0.2, so it's 0.5, 0.2. 12 to 6, we go down 6, so that's minus 0.6. And then to do the endpoints, we can't stick it in the middle, so we do the best we can. So we go up 2 over a run of 5, so that might be 0.4. And down here we go down 5 over a run of 5, so it's like minus 1. Okay. The other great process we did was we looked at its antiderivative. So now we could say, well, what happens if we integrate f of x? Okay, and so to come up with numbers, we've got to put bounds on this. So we might say 0, put 0 down here, and then to turn it into a function, we could let that variable vary, right? Oh, hang on, I'll put the x up here. Okay, so this is some function, the antiderivative. So how do we go about doing something like this? Well, what is going to be the integral from 0 to 0 of any function? What's the area under a rectangle with no width? 0. Exactly. So we can. Okay. So now if I do a 5 here, what am I going to do here? Well, what I'm going to do here is I want to figure out how much over here. Well, I'm going to here I've got, so my function f looks like what? It looks, kind of looks like this, right? And so here I've figured out what the slope is at any given point. And that's what those numbers here. Now to take the antiderivative, I've got to figure out what this area is. Okay? So here the height is 7, here the height is 9, the base is 5. So the left-hand sum is 7 times 5 is 35. The right-hand sum is 5 times 9 is 45. We take the average and we get 40. Okay. 0 to 10. We now do the same thing, but now we go up to 12, let's say. Well, if this guy here was 40, if this was 9 and this is 12, then in this rectangle here, it'd be 5 times 9 is 45. 12, 5 times 12 is 60. So taking the average of those two would be 52.5. So this region here, I'm going to estimate to be 52.5. I add it to what I had before, and I get 92.5. I can do this another time. Oops. The thing looks a little like this. 11. Right. So this, in this rectangle here, it's 60. And 5 times 11 is 55. So I take the average of that, and it's 57.5. I add it to this guy here. What do I get? 150. And then finally, here it's 6. So 6 times 5 is 30. The average of 30 and 55 is 85, is 42.5. I add it to this and I get 192.5. Okay, so these were the two different basic processes that we did. We had the process of finding a slope, which was just rise over run, and we had the process of finding area underneath a curve by using rectangles. We could do the same thing with graphs. So let's see if I can. Well, maybe I can. Like that. Let's see if we can use this board here. So let's say we do in a graph. And I'm going to try and be a little bit careful so we can actually make some figures. So I'm going to put in a grid of points. I'm doing it too fine. And then I put in a function. So that's and so now here is my f of x. We can do the same kind of thing that we did over here, except now we're doing some geometry. So now we need ruler and pencil to measure things. And so at each of these points, what we can do is, well, we can say at 0, we can put in our ruler and we put in a tangent line like this, and we see that, okay, it seems like we rose 3 over a run of 3, so the slope is 1. Okay, so it's the same kind of process, except we use We're still figuring out slopes. We're still doing rises over runs, but now we have to measure them ourselves. At this point here, let's say this point here, that's 3. We see we have a straight line. And so we see that f prime of 3 is 0, etc. So you should definitely try and bring a ruler to the test. They're useful. Now to do integration. You still need some kind of bounds. And so now, for example, to do this, we would figure out what this area is here. So one thing you can do is turn it into a numerical problem, right? Figure out what those values are and do the same thing you did over there. Or you could go ahead and you could just start counting squares, right? So here's 1, 2, 3, 4, 5, 6. And then we've got this guy here. There's a 7. Okay. There's an 8 if we borrow stuff from here. And then we've got that, and that looks like to be around a 9. So however good we are at measuring things, how good our eye is, how straight our ruler is, if we're careful, we can come up with estimates for that. Okay. Finally, we've got formulas. And that's kind of what we spent the most time on, is doing all the kind of tricks to take. Mainly we did derivatives. We only did antiderivatives, integrals just a little bit, not as well as we did derivatives. So just remember all our different rules. Okay, so so firstly, we had rules about how to take derivatives of various functions. So that we had a power rule. We had an exponential rule. We had derivatives of log. We had trig functions. Do you have anything else? Anyone remember anything? Any other? So that was one kind of rule. So we know how to take the derivatives of certain pieces. Then we had the rules of how do we take the derivative of a combination. So an important one was the fact that derivatives are linear, right? So this is equal to like the derivative of a sum is the sum of the derivatives, the constant multiple of a derivative is the derivative of the constant multiple, that kind of stuff. We had a product rule. Quotient rule. Was what? Low, P high, I, low, 1 squared. And the most important rule of all was the chain rule. Is the one where we get to multiply chain derivatives together. And with this, we could really take the derivative of any kind of complicated function we liked, right? So for example, x squared times e to the sine x, for instance. Okay, we could take the derivative of that, right? So first, we had to read it. So first, which rule do we apply first? So what is kind of like on the outside?
You just like make the 2 when you take out 2x.
Right, but that's later on. What do we do first of all? What's the first rule we apply? Before we do that power rule, we've got there's things that occur before the product, before this power x squared. The product rule, right? So it's going to be x squared times the derivative e sine x plus 2x times e and sine x. Right, and so as part of doing the product rule, we have to do the power rule. This guy here is just a chain rule, right? So that's going to be x squared times, well, the derivative of an exponential is an exponential. This bit, then we take the derivative of what's here. And then finally, we take the derivative of sine x, which is cosine x, and we get x squared cosine x e to the sine x plus 2x e to the sine x. Very complicated, but I hope you see the logic behind it. So as long as you see the logic in which order you do things, you can always do these kind of derivatives. And you can tidy this up a little bit, but I wouldn't for the test. Unless, right, I was asking for where the maximum is, for example. Then I would factor this. So I pull out an x. I pull out an e to the sine x. I have left x cosine x plus 2. Right, and this would have a critical point at x equals 0. And where this equals 0? 1. At 1. At 1, why 1?
Is it cosine of x?
Yeah, that's a complicated one. You actually have to graph that one to figure that one out, because when x is 1, that whole thing is not 0.
Oh, it's not multiplying. Yeah.
It's x times cosine x, right? So it's going to be when x times cosine x is -2, and we can't solve that directly. You need a calculator or something to estimate what that is. So you have to put it on your graphing calculator to figure out what that is. Okay, but if the question was just take the derivative of this, that's a perfectly good answer in the test. So what good are derivatives for? Okay, so I would answer in two ways. One is it helps us understand the function. So knowing the derivative of a function tells you when is the function increasing and where is it decreasing, right? Because that's where the derivative is positive, where the derivative is negative. That's the most important information that a derivative gives. Also tells you where the function is flat, right? Those critical points. Okay? And that goes into the second reason why derivatives are so important. Where derivatives are flat, they're potential critical points. So that's where you can have your maxes and your mins. With integration, we are really much less sophisticated. Okay, really, any function I give you, you can differentiate. You just pick it apart, figure out how it's put together, and just use the corresponding rule to take its derivative. With integrals, you've got much less machinery. Okay, and so you've just got to recognize, so what things do we know? We know, for example, we have a power rule for derivatives where we add 1 to the power and divide by that. We've got that pesky plus c. And we can do this as long as n is not equal to -1, because the integral of x to the -1 dx is ln of x plus c. For exponentials, this should make sense, right? Because when we take the derivative of this, what happens? The plus c disappears because the derivative of a constant is 0. When we take the derivative of this, the derivative of an exponential is an exponential, but then by the chain rule, we have to multiply by k, and the k's cancel, and we end up where we started from. And also, sine kx dx is minus cosine kx divided by k plus c. Really, the only rule that we have for integrals about how to take an integral of a function that's been put together is we've got a linearity rule like we have for derivatives. That's equals a times the integral of f of x dx b times the integral. So you can see there's much less functions that you can integrate than you can differentiate. But that'll be on the test. So the functions that you'll be given to deal with derivatives are going to be harder than the ones that you're going to integrate. Okay. So hopefully you'll know how to differentiate any function really that I give you. you can handle that. You'll also be able to handle anything I give you to integrate that because it's going to be a simpler function. So I'm going to give you for integration. Okay, what are the uses then? So we've already talked about derivatives, how they're important because they tell you how the function behaves and how you can find critical points and find maxes and mins. We talked about the second derivative. So the second derivative, remember, is the rate of change of the rate of change, and that will give you concavity. So the function's concave up or concave down. And that helps with finding maxes and mins too, right? Because a max is going to be concave up, so it's going to concave down, sorry. So it's going to have a negative second derivative, while a minimum is going to be concave up and it's going to have a positive second derivative. We talked about inflection points, and that's where a function changed concavity. So for instance, here's a very simple example. Let's compare x squared, x cubed, and x fourth. What do the derivatives tell us about these functions? I mean, these are functions we know very well, but if we take the derivatives, right, we get 2x, 3x squared, 4x cubed. So all of them have critical points at x equals 0. Let's classify them. Okay, so x squared, the derivative is 2x. What happens to the sign of the derivative as x goes through 0? Does it change? It does, right? It goes, when x is negative, the derivative is negative. When x is positive, the derivative is positive. So that means it goes down and then goes up. So this is a min. This doesn't change sign, right? It's positive beforehand and positive after. So this is neither max or min. And then this one is like this one, it goes down, then up. And this is a min. What about the second derivatives? This is 2, this is 6x, this is 12x squared. Inflection points. This has none. It doesn't have even any candidates. X equals 0 is a possible candidate because the second derivative is 0. And here x equals 0 is a possible candidate. But to be an inflection point, it needs to change concavity. Does this change sign as it goes through 0? Yeah, right? Before it's negative, afterwards it's positive. So it goes from concave down to concave up. So that is an inflection point. What about this one? Does it change sign? It doesn't. Okay, before it's positive, afterwards it's positive. So it's concave down before, and it's concave down afterwards. There's no change in concavity, not an inflection point. Okay. So you see that it very much depends upon the power, whether the thing changes sign or not. So if it's an odd power, it is, and you're going to have a change. If it's an even power, it's not going to change sign. So it's not going to be an inflection point or a max or a min. Okay, so that was a basic example, but it's the same logic that you do for other things. We did a lot of stuff with economics. Okay, so we did a whole lot of things about things like elasticity. What else did we do? Present value. Consumer and producer surplus. Okay. Everyone, I'm not going to review that because everyone actually did pretty well. So it seems like everyone knows those concepts pretty well, but I would still review it. Any question I ask about it's only going to be a short question because it's going to be in the comp. All this stuff, I'm only going to be asking short questions on this material. We had logistic growth and the surge function. So with logistic function, it's this S kind of function. So it kind of looks like this. What are the important things to know about the logistic function? Firstly, there's a carrying capacity, right, which is kind of like the limit of the system. And that's kind of like a horizontal asymptote. For low values, it's like an exponential. High values, we have this horizontal asymptote. Anyone remember what's the other important fact to remember about the logistic function?
The point in the middle. The inflection point.
Exactly, it's the inflection point. That's where it changes from the exponential behavior to the horizontal asymptote behavior. It's kind of like flipping a switch. And it's the point at which it's growing fastest. The other kind of function we talked about was the surge function. So what was this? This was like x e to the minus bx. What's this point here?
Heat concentration, like the maximum.
Yeah, and it happens at 1 over b. So that's the important fact to remember about that function. Okay, that's kind of the main things that I wanted to mention. Questions? Anyone wanted a particular example of anything or wanted to go over anything? So that was my rush tour of what I consider essential in the course. And it's what I'm going to concentrate on the test on. No one? Okay. So then we can think. So tomorrow we're going to have presentations. I think your team, you just always impress me as being the most organized. So you can go the first. Okay, and then the other guys can go in afterwards. So you're going to make like a little PowerPoint presentation?
Yeah, it's actually like ours right now, we have about 3 slides of information, but I mean, it's not going to be very long, but we kind of just like have all the stuff we need there. So
yeah.
And then we'll have our write-up to hand it to you.
Yeah, yeah. So just take you just answer the question. You don't, yeah. I don't really have like a set time. It's just answering the question.
Okay, yeah, that's what we did.
Okay. See you, Jinru.